All right, exam 3, problem 4. Here we have an aircraft. The wing should produce 1,000 newtons per square meter, or 1,000 pascals, right? At takeoff, it travels at 60 meters per second, so the airspeed relative to the bottom of the wing is 60 meters per second. Given the sea level density of air, how fast must the air move over the upper surface to create the ideal lift? All right, so let's put down Bernoulli's equation. P equals P1 plus 1/2 the density times g times the velocity squared. Pardon me. Right? Velocity 1. And velocity 1 is the velocity at the bottom of the wing, right? We're calling that the velocity at the bottom of the wing. And then when P2 plus 1/2 rho V2 squared, right? Now we're talking about the pressure on top of the wing and the velocity of the air across the top of the wing plus rho G H2. Now, essentially no difference between H1 and H2. We're going to simply, for the moment, say we're just going to let rho G H1 equal rho G H2 and not worry about that term, right? Not going to worry about that term. It goes away. And so we're left with P1 over plus 1/2 rho V1 squared plus P2 equals P2 plus 1/2 rho V2 squared, right? All right. Well, I'm going to rewrite this just a little bit as P1 minus P2 equals 1/2 rho V1 squared plus, V2 squared minus 1/2 rho V1 squared. Right? Now, the reason I did this is because we know P1 minus P2, right? We need for P1 minus P2 the net pressure up, which is pressure from the bottom minus pressure from the top. We need for that to be 1,000 newtons per square meter. All right? All right. And that means, and we know rho, because rho is 1.29 kilograms per cubic meter, and we know V1 is 60 meters per second, and so we're after V2, right? We're after just V2. So I should have left V1 on the other side. I didn't. So 1/2 of rho V2 squared is P1 minus P2 plus 1/2 of rho V1 squared. All right? What we have to do is isolate the unknown V2. I'm going to divide by 1. I'm going to multiply by 2. I'm going to divide by rho. And that's going to give us V2 squared is 2. I'm going to just write this as delta P. All right, let me go back up here. I'm going to write that as delta P, 2 delta P, plus rho V1 squared, except I also divided by rho. So that goes, that rho, it's just V1 squared. And I need to put after delta P, a divide by rho, right? So 2 delta P over rho plus V1 squared. All right, and the final little bit, we need, just take the square root to get V2 equals the square root of, I'm just going to go up here and copy this. See how that works out for me. All right? V2 is the square root of all that stuff. All right, so how do we calculate this? V2 equals the square root of, okay, 2 times 1,000, 2 times 1,000 divided by 1.29 kilograms per cubic meter. 0.29 kilograms per cubic meter. All right. And I need a 9 in there, don't I? 29. And plus, it's our velocity, 60. All right. Plus 60 squared. And our units at the end of the day are meters per second, right? So 2,000 divided by 1.29 plus 60 squared, take the square root. All right, so I'm going to put in 1,000. I'm going to put in 1,000. I'm going to put in the 1.29. I'm going to put in the 60. All right, so I'm first going to calculate 2 times 1,000 divided by 1.29 plus 60 squared. Double check that. Okay. And now we're going to take the square root. All right. So we get that the velocity across the top of the wing needs to be 71.8 meters per second in order to reach the lift that we want with 1,000 newtons per square meter. Okay. All right. So part B. How fast must the air move on the upper surface if the cruising speed is 245 meters per second and air density is 1/4 that at sea level? All right. So part B. 1 rho equals 1/4 of 1.29 kilograms per cubic meter. Right. And V1 is now 245 meters per second. Okay? And the question is, now the exact same equations apply. We're still talking about P1 minus P2 is 1,000, right? So all the algebra is exactly the same. We're going to end up with exactly the same equations. Let's figure out 1.29 divided by 4 is, all right, 0.3225. 0.3225 kilograms per cubic meter, right? All right. So if we just stick that into the same equation, we'd be looking at 0.3225 here and 245 there. All right. So what does that bring us to? I'm just going to go up here and I'm going to put in 0.3225 and I'm going to put in 245 for that velocity, and that's going to give us a velocity of 257 meters per second across the top of the wing in order to provide the lift we want at 245 meters per second across the bottom wing. And that's it for problem 4.